languages A in P space are reducible to that language in polynomial time, right? So today we are going to see how certain languages based on games are P space complete. Okay, so in the previous lecture we saw that the language TQBF, true quantified fully quantified Boolean formula, is P space complete. So the first language that we consider in this lecture is what is called formula game, and it is very closely related to TQBF. Okay, so what is the formula game? It is that there are two players, let's call them Alice and Bob, or player 1 and player 2, and they are given a Boolean formula with many variables, and they take turns. So the variables are x1, x2 and so on, they are labeled, and they take turns trying to assign the true and false values to the variables. And of course it won't be a game unless they have conflicting objectives, right? So the player 1 wants to make the formula true and player 2 wants to make the formula false. So just to be more formal, so it's a game like this. So phi is a quantified Boolean formula like this. There exists x1 says that for all x2 there exists x3 something psi, and where psi is an unquantified Boolean formula. Okay, so they are both trying to assign values to Boolean values to x1, x2, x3, etc., such that player 1 is trying to make psi true by setting the values, player 2 is trying to set psi to be false. Okay, so player 1 wants to make it true, player 2 wants to make it false, and they take turns assigning the variable values. So let us try to see this one formula. Let's say phi is this. There exists x1 such that for all x2 such that there exists x3 such that this is true. Let's see what happens in this case. Now let's say if player 1 sets x1 to false. Okay, so now that means that this is a CNF form, right? So the first clause is already has to be made true. So player 2's objective is to make the entire formula false. So player 2 can immediately set x2 to be false, and then the entire formula is false, right? So player 1 should do something smarter. Player 1 should set x1 to true. Now once player 1 sets x1 to true, right? So again, just to recap what I said, if player 1 sets x1 to false, then player 2 can set x2 to false, and then the entire formula is false. So that leads to a lose for player 1 and win for player 2. Now if player 1 sets x1 to true, so the first clause is already true. Now what can player 2 do? Let's say player 2 sets x2 to true, right? So then the second clause is already true now, and part of the third clause is false because x2 complement goes to false. Now but then player 1 gets to choose x3, and he can choose x3 to be false so that x3 complement is true. So the entire formula gets evaluated to true, right? So player 2, if he sets x2 to true, then that does not lead to a win for player 2, that leads to a win for player 1. Instead, if player 2 sets x2 to false, second clause is now not true, but third clause is set to true because x2 is false. Now all the player 1 has to do now, player 1 again has control over x3, but he doesn't need to worry about clause 3. All that he has to do is to set clause 2 to true. For that he can simply do that by setting clause x3 to be true. So now it's very clear. So if x1 is set to true, then player 1 has a winning strategy here. He sets x1 to true. Now depending on what player 2 sets the value of x2 to be, he can choose x3 to be the opposite of that. So if player 2 sets x2 to false, then x3 is set to true, and if player 2 sets x2 to true, then player 3 can set x3 to false. So either way there is a win for player 1. Okay, and there is a winning strategy for player 1 means player 1 can always win, which means there cannot be a winning strategy for player 2, right? If I can always win playing this game, then my opponent will, whatever he or she tries, cannot win the game, right? So, so now this is the game, and maybe it is. So now you can see when x1, x2, x3 are kind of alternating between player 1 and player 2. Now this is exactly like for TQBF, right? So we are just asking whether this fully quantified Boolean formula is true or not, right? So that is, so what is formula game? Formula game is a set of all, again I have not formally defined it. Formula game is a set of all Boolean formulas phi where player 1 has a winning strategy, right? Player 1 has a winning strategy. Right, and player 1 has a winning strategy when this fully quantified Boolean formula is in TQBF, right? Because this fully quantified thing has to be true for player 1 to have a winning strategy. So that's why the formula game is also, so it's essentially equivalent to TQBF. So this is also p-space complete. Right? It's essentially the same game, but just being kind of interpreted as a TQBF was something about Boolean formula, but this is just more interpreted more as a game than Boolean formulas, right? So maybe just to give a bit more insight, let us try to see this like game tree, right? So initially x1 is going to be set, right? So it could be set to 0 or 1 or true or false, and then x2 can be set to true or 0 or 1. Then x3 can be set to 0 or 1, right? And now we are at different places. So if x1 and x2 are both false, then I think, as we discussed initially, both these lead to false. False meaning player 1 is losing, right? Player 1's goal is to make the formula true. If x1 is false but x2 is true, again this is something that we didn't explore, x2 is true, then now again there is a winning, it depends on what x3 is. If x3 is 0 or false, then the formula is correct, is set to true, otherwise it's false. And if x1 is true, then now x3 is set to just opposite of x2. So this is false, this is true, and this is false, and this is true. So now, sorry, it's the opposite is a win for player 1. So now you can see this game tree and see what is happening, right? So there's another way to explain the whole thing again. So player 1 wants to go to a place such that no matter what player 2 does, player 1 has a winning strategy. So let us see. So if player 1 had taken this path, this path, setting x1 equal to 0, then player 2 could lead player 1 to x2 by setting x2 to 0 to this point. Now no matter what player 1 does, it leads to false. It leads to a lose for a player 1, right? So it is like this. You could for these levels just above the leaf. Now that we know that the last turn is by player 1, you could see what. So if player 1 gets it in this node, right, this node over here, it is a false, right? Meaning whatever player 1 does, he cannot win. But if he gets it here, it's a true. Maybe I'll use another color. So this is false, and this is true, because from this there is one path, and here also true, and here also true. From these points there is one path. But look at this now. Look at player 2's turn at x2. Now maybe I'll use another color, green. Now over here it's a win for player 2 because he can guide player 1 to the false place. So this is also a win for player 2, which is false in our terminology. Right? So false true is absolute, win for player 2, win for player 1 is relative to player 1, player 2. But the right subtree, sorry, it is a win for player 1 because no matter what player 2 chooses here, it leads to a win for player 1. Right? And at the top it's a win for player 1 because now player 1 gets to choose. So now there is a false and true, he can always go to the true. So now this is how you evaluate a game tree. So at the place where player 1 has to decide, he just needs one path of a victory. At the place where player 2 has to decide, if player 1 is to win, all the paths should lead to victory for player 1. Right? So that happens in this tree. So this is a victory for player 1. Is there a way to modify this so that you can think about it, right? So this is how you view games as trees. Again, these are simple games which you can compute. And this is the formula game. And just one more final point. Here we had players taking turns, x1, x2, x3 and so on. But it need not be turns like that. So player 1 could have one or maybe two variables, maybe three variables. Two variables player 1 plays, followed by three variables played by player 2, followed by x6 by player 1 and so on. It could be like that also. You could get a corresponding tree there also, but then more choices will be made by one player. So it will be a bit different, but it is still the general principles of what I said just continues to hold. Okay, so this is how you view games as trees, right? So formula game is another piece space complete game. Another piece space complete game is what is called generalized geography. Okay, so what is geography? So geography is kind of a very it's kind of like Antakshari that some of you might have played as kids. So the goal here is to, let's say player 1 says, or let's say two players, okay, you could have more players, but for simplicity let's stick to two players. Let's say player 1 says the name of a place, right? So let's say Hyderabad. Now player 2 has to say the name of a place which starts with the last letter. So player 2 could say Dubai, let's say. Now player 1 has to say a name of a place that starts with I. So let's say player 1 says Istanbul. Now player 2 has to say something starting with L. Let's say Lucknow. Let's say player 1, 1, 2, 1, 2. Player 2 has to start with W, maybe Washington, right? So on, right? So this is just how it is. So after player 1 says Hyderabad, player 2 could have said, say, Denmark, for instance, right? And player 1 has to say something with K, so he may say Kozhikode. Right? So this kind of thing is what, and this game continues till some player cannot say, cannot name any place with the assigned letter, right? So this is the game Generalized Geography. This is the game Geography, sorry. This is not generalized. The generalization hasn't happened yet. But this is the game. But what is generalization? The generalization is that, now this is, you can, like I have drawn here, you can view it as a graph, right? And player 1 makes a move, then player 2 makes a move, and finally the person who cannot make a move loses, right? So the multiple ways to reach each place. So let's say from Dubai you could have said India, which is another name of a place, or Indonesia, right? From Indonesia you could have said Afghanistan, right? So from Afghanistan you could have said New York, for instance, right? So from New York again, maybe again you could have said Kozhikode or Calcutta or whatever, right? So on. So again, there are different ways to reach the same place. So the generalized version of this game is where you have, again, this is also there in CIPSR, again where you have a graph. Okay, I'm just reproducing the same example in CIPSR. Okay, so player 1 starts with 1 and it is his turn, and he could, I'll just draw the arrows and then talk. Okay. Right, so now let's say player 1 starts from 1, right? So now in this graph, the goal is to leave a person without a move. So player 1 can go to 3, and now player 2 can now, there's only one move from 3, there's only one outgoing arrow, so he has to go to 5. Now player 1 can now go to 6, and player 2 is stuck, right? There is one outgoing arrow from 6, but that goes to a place that has already been visited, right? So you again, the name in the geography game, you cannot name a place that is already named, right? So here 3 is already visited, so that is ruled out. So player 1 wins because player 2 is left without a move. Okay, so this is an example of a graph where player 2 does not, player 1 has a winning strategy, right? So maybe I'll just write define the game formally. Generalized geography is a graph G and a starting position B such that player 1 has a winning strategy starting from point B at or in the graph G, right? So this is the definition of the game. So as I said, if in this graph player 1 has a winning strategy, the goal is to identify who has a winning strategy, right? So let's say we change the graph a bit and we reverse this edge, right? So now it turns out that player 2 has a winning strategy. Why? Because let's say player 1 plays to 3, right? Now player 2 can lead 1 to 6 and there is no outgoing arrow from 6, so player 1 has lost. Okay, so this is why player 1 cannot play 3 first. What if player 1 plays to 2, right? If player 1 leads to 2, then player 2 can move to 4, right? Now player 1 is again he is not stuck, but he has 2 choices. So player 1 could move to 7 or 5. If he moves to 7, then player 2 can push him to 9 without any exit point. If he moves to 5, then player 1 can push him to 6 without any exit point. So this is a graph where no matter what player 1 does, there is a strategy for player 2 to win the game. So this is not an instance of generalized geography, or this is no instance of generalized geography, right? Whereas if this red edge was reversed as I had drawn initially, that's a yes instance. So Again, in games like this where the game is finite, right? So here it's a finite game. There's a finite sequence of moves, right? It is a finite game where the win and loss are absolute, right? So either A wins, player 1 wins, or player 2 wins, right? There are no draws. In such games, either one of the two players must have a winning strategy. It cannot be that, because you can look at the game tree and do the analysis that I said earlier, like the game tree over here or something like this, right? You could do the analysis that I said earlier and determine who has a winning strategy. So in games like this, one player has to have the winning strategy, and if one has a winning strategy, two cannot have the winning strategy, and vice versa, right? And this game of generalized geography also turns out to be p-space complete, and the proof is there in CIPSR. I'm not repeating the proof here, but it's kind of a long proof. Generalized geography is p-space complete. Proof is there in CIPSR. You can take a look, right? And so this is also another game that is p-space complete. So now let me just talk about games in general, right? So again, like I said earlier, why do all the games have to have a winning strategy? All the finite games. So suppose the game tree is like this, okay? So like what I've drawn here. In this game, who has a winning strategy? This is a very simple game with just two moves. Player 1 makes a move followed by player 2. So player 1, where will he move? Let's say the W's denote wins for player 1 and L's denote loss for player 1. Player 1 will take the middle path, right? This path, because then whatever player 2 does, whichever three next directions player 2 does, player 1 is going to win. However, if we change the graph slightly, very slightly, let's say change this W to L. Now whatever player 1 does, right? Whatever player 1 does, whether he goes for the first, let's see, he goes here, then player 2 can push him down here. Let us say he goes to the middle path, then player 2 can push him down to this. And if he goes, player 1 goes here, then player 2 can go anywhere. Let's say player 2 goes here. So now in this case, player 2 has a winning strategy. But in the earlier case, when this L was not there, instead it was W, player 1 had a winning strategy. So in general, all the finite games where there are no draws, one player has to have a winning strategy. So in that sense, even games like chess, right, are finite games. Okay, even though chess has a possibility of draw, they are finite games, right? Because there are rules of chess that prevent the game to continue infinitely, right? So for instance, if a position appears 3 times, then it's a draw. Or if a position does not appear 3 times, then something has to keep changing. So maybe after a while you run out of pieces. So then the positions will not repeat. So the game, because of the rules, is inherently finite. So chess, you can analyze it in this manner. Maybe the analysis will be more complicated because of the fact that the number of positions to analyze is humongous, even for a computer as of today. Right, so it's so complex that you cannot analyze that. But in small games like tic-tac-toe, right? So you can certainly analyze, and I think there are you could easily find the perfect strategy. If both player 1 and player 2 plays tic-tac-toe, then it will be a draw, right? So this is about chess or any finite games. They will have you can study it, but then the point with chess is that it's so complex, right? It's even for a computer, it's so hard. And then it's another thing for, let's say there is a winning strategy for the white in chess. Now, in an actual game, in an actual championship, when a person is sitting across the table of another person, and then you don't expect, even if there is a winning strategy, it could be so complex that somebody cannot remember all that, right? So that's why it's one thing to show that it is a win for white or win for black, but then it's another thing to execute it. But anyway, as of now, even computers don't know whether it's a win for white, win for black, or a draw. Okay, I think checkers has been shown to be a win for a draw. I think the game checkers, where it's simpler than chess, so but still played on an 8x8 board. So games in general are p-space hard. Okay, what do I mean by that? Like we said, generalized geography is p-space hard. Like a specific game, if I give you a graph, a specific graph, you can decide. But then in general, this problem is p-space hard. So what is generalized chess? So as I said, chess is a finite game, 8x8 squares and fixed number of pieces, etc. But generalized chess is let's say played on an n cross n board and with maybe different rules for the pieces, maybe more pieces, etc. Right? So the question is, given some n cross n board with some specific pieces, is it a win for a white or black? Right? So this turns out to be p-space hard. The reason is what we said earlier for all these generalized geography, formula game, all that. You could encode given that you could encode the entire thing into a formula. And then you are asking, is there a move for player 1 such that whatever player 2 does, such that there is a move for player 1 again, such that whatever player 2 does, etc., such that it leads to a win, right? So this entire, whatever is the n by n generalized chessboard, you can condense it into a Boolean formula. The position can be captured into a Boolean formula. And then this position now, it just becomes kind of, once you represent the win losses, it just becomes like a formula game kind of thing. Again, I'm just speaking in a very, very high level. It sounds like I'm oversimplifying things, but this is a high level idea. And indeed, it has been shown that generalized chess is p-space hard, and as are generalized forms of many other games. Okay, so many games are p-space hard. Like many games, when I say generalized games, like not fixed. Like tic-tac-toe is a finite game, so obviously you know the rule. You know that it is the perfect strategy leads to a draw. And like once you give a fixed graph, one can determine. But the problem is, in general, if I am giving you a graph or giving you a board, the problem of analyzing who wins or who loses, that is p-space hard. Yes, so that's about what I wanted to say in this lecture. So just to summarize, formula game is kind of identical to the TQBF, and it is a p-space complete. Generalized geography is a generalization of this geography game, which is like Antakshari, which is the generalized form of which is p-space complete. Again, I didn't show the proof, but you can read up the proof from Sipser. And in general, I just talked a bit about games and why for finite games one person has to have the winning strategy as long if there are no draws, right? And I said that the generalized games, where the generalization of a certain game, like generalized chess, it has to be p-space hard. So the generalized chess is p-space hard. Sorry for the bad handwriting. Or p-space complete. And yeah, that's all I wanted to say for this lecture. So I'll stop now. Thank you.
Swayam Prabha, Digital India, Educated India.
Hello and welcome to lecture 21 of the course Computational Complexity. In this lecture, we will see space hierarchy theorem, right? So in lecture 13, we had seen time hierarchy theorem, right? And let me just recap. Time hierarchy theorem basically said that if you have more time, then you can compute certain languages or problems that you could not do if you did not have that more time, right? So having more time certainly helps, right? That is what we could infer from the time hierarchy theorem, right? To be more precise, let me just write once again. To be more precise, it said that if Gn log Gn was little o of Fn, then the time Gn is strictly contained in the time Fn. Okay. Basically, if you have more time, then you could compute certain functions or certain languages which you could not compute if you had the less time. So space hierarchy theorem is going to be very similar, just that time is going to be replaced by space. And even the proof technique that we are going to use is going to be very similar. So if you may recall that we had defined time constructible function. Similarly, for the time constructible function, we defined for the time hierarchy theorem. Similarly, we will define a space constructible function. So what is a space constructible function? Basically, it is a function Fn such that Fn itself can be computed in Fn space, right? So the space required to compute the function is equal to the is at most the function itself, right? And a bit more technical detail is that the input should be given as a unary string, as a string of ones, the number of ones being the input n, and the output should be the actual function, right? Because we have to write in unary the input because usually the input length is always n, right? So here we want to write the input in unary, right? So this is the definition of space constructibility. Basically, a function Fn should be computable in the space bound given by the function itself. Time constructible was exactly the same, just that you had to replace this space bound with a time bound, right? And like I said, for time constructible functions, most of the familiar functions that we have, like n squared, n log n, square root n, log n, everything, all of this is space constructible. You will have to think of really obscure functions to get something that is not space constructible, right? So maybe one exercise that you can try out, why is log n space constructible? Can you see how to compute given n or given n ones in a string? How can we compute log n in using at most log n space? Okay, you can try that. So now let me formally state the space hierarchy theorem, right? So for any space constructible function f, right, there is and a function g such that Gn is little o of Fn there is a language A that is in D space Fn sorry, but not in D space Gn. So Fn is a time constructible, space constructible function, and consider a function that is little o of Fn, meaning little o means limit Gn divided by Fn tends to 0 as n goes to infinity, right? So Gn grows at a strictly smaller pace than Fn. Limit Gn divided by Fn goes to 0. In such a case, right, there is always a language that can be decided in Fn space but cannot be decided in lesser space than that, in Gn space, right? So just to formally, or to state it in another way, so if Gn is little o of Fn and Fn is space constructible, then D space of Gn is contained, but strictly contained, in D space of Fn. Right? So this containment is strict. This is what space hierarchy theorem means. So just to contrast this with time hierarchy, it's exactly the same, just that in the time hierarchy theorem we required Gn log Gn to be little o of Fn. Over here we just need Gn to be little o of Fn. So there was a gap of log n that was required in the case of time hierarchy theorem. In the case of space hierarchy theorem, we don't need that. So even things that are very close, very close, closer than log n, but as long as they are little o of Fn, it's fine. So for instance, if, like, let's say Fn is n squared, or let's say Gn is n squared, and Fn is, let's say, n squared square root of log n. Even in this case, D space of Gn is strictly contained in D space of Fn. Whereas we cannot use the same G and F for time hierarchy theorem, because this does not have a gap of log n. This G and this F, we need a gap of log n, which is not there for this G and this F. We cannot use these two functions to get a gap in the case of time hierarchy theorem. Right? So that is a statement. What is the proof idea? The proof idea is also, idea is also very similar to that of time hierarchy theorem. So I'll present it slightly differently, so that maybe sometimes when you see multiple or slightly different way of presenting the same thing, it helps the understanding better, right? So you may recall that in the case of time hierarchy theorem, we used diagonalization, right? So we first saw the proof of the halting problem, or the acceptance problem, and then we saw how to modify that, how to adapt that for the time hierarchy theorem. So here, since we had only recently recapped that for the time hierarchy theorem, I'm not going to recap the proof of the halting problem, but I'll just use the same, but then the techniques are exactly the same. So what did we do in the case of time hierarchy theorem? We basically had a machine that simulates another machine. So if you recall, we wanted to show the separation between n and n squared. So basically we would simulate an n machine with in n squared time, right? Sorry, n power 1.9 time, right? So this is what we had. So whatever input we get, the input being a Turing machine, we just simulate the machine on its own description for n power 1.9 steps, and then reject and flip the output, right? So here, so basically we simulate the machine on its own description and then flip the output, while making sure the time was at most n power 1.9. In the case of, so here we will, one change in the presentation is that here we will stick to abstract functions and not specific functions like that, because we have already seen it. So maybe I would like everybody to be comfortable with this abstract function. So we will not use concrete functions. And second point is that we wanted to show that we wanted to run for n power 1.9 steps, which is something less than n squared but more than n. So here we will try to do the same thing but with space. So we will make sure that it takes adequate space but no more than fn, right? So it runs, so we will try to simulate a gn space machine with an fn space machine, but we will have to curtail the space usage. So that brings in a small difference on how this implementation is done. And again, to answer the earlier question that I myself had asked, in the case of time hierarchy theorem, we have this log n factor, right? This one, which is not appearing in the space hierarchy theorem, right? There is no log n here. Why is that? If you recall, in the time hierarchy theorem, we had used a certain result that to simulate any Turing machine with its description by Henney and Stearns, right? Which said that any Turing machine that runs in time t needs t log t time to simulate by another Turing machine, by a universal Turing machine. But however, in the case of space restricted Turing machines, we can simulate it, and there is no need of this extra log factor. So that extra log factor does not appear in the equivalent simulation of the space bounded machines, and that is this extra log factor that we are saving in the space hierarchy theorem. Okay, so now let us get on to the idea. The main idea is to construct a deterministic Turing machine that simulates all the gn space machines and flips the output, right? And then flips the output. And so, and whatever is a language accepted or recognized by the Turing machine that we construct, that will be the language that is in d space fn but not there in d space gn, right? So basically what we do is we first check whether the machine first checks whether so the input is read as a description of it is interpreted as a description of a Turing machine, right? So you could describe that Turing machine. So is it a description is first checked. This is something that is straightforward. Are there states, are there transitions, and so on. If it is a description, if it is not a description, it is immediately rejected. If it is a description of a Turing machine M, say, okay, if it's a description of M, then what it does is it simulates the machine M on its own description, right? So if it is a description of a Turing machine, so then D simulates the machine M, so on the description of M, right? So this is the description of the Turing machine M, right? So this is used to, this M with angular brackets is used to denote the description of the Turing machine M. So it simulates M on an input, so the input could be anything. So here we are simulating it on its own description and then flip the output, right? And there are some things that can happen. One is that the machine may not halt, right? How do we deal with that, right? And second is that it may take more than the allotted space, right? So we want D to be an Fn space bounded machine. So these two things have to be prevented, right? It not halting and it taking more space. In the case of time hierarchy theorem, we stopped the simulation at a certain point, right? Because we wanted the time to be bounded. But here it's not a time bounded machine. So how long do you keep simulating? So this doesn't halt problem. How do we stop it, right? So we'll address both. So what we'll do is so the question is, how do we check these two, right? This and this. So one is, so one meaning this one, the doesn't halting, not halting. So we will use, we will use a counter based time limit, and for 2 basically we want to constrain the space usage, right? So we will just mark some cells as unbounded, like as you cannot, as out of bounds, right? So mark the tape cells as out of bounds. So basically we say which is the territory that the machine can operate. And there is another, so these two handles, these two solutions handle these two issues. The another thing is that this was also there in the case of time hierarchy, but perhaps I didn't elaborate to this detail so as to not cause any confusion, because I wanted to make it essentially the diagonalization. So now that we have seen diagonalization, I just want to bring out this particular issue. So one is that even though Fn is or Gn is little o of Fn, right? It could so happen that for small values Gn could be higher, right? So what I am saying is, so the graph could be something like this. So this could be, maybe the red is Fn and Gn could not like this, but maybe something like this. Let's say this is Gn, green is Gn. But for small values, so in this case, it is possible that Gn is little o of Fn, right? So maybe what I have drawn looked like a constant, but maybe there is this needs to taper off slightly, okay, something. But the point here is that in this region, right, in this region, Gn is greater than Fn, right? So in this shaded region. So, but that's okay, because all that the asymptotic says that if Gn is little of Fn, at beyond a point this should happen. Gn should be less than some constant times Fn for any constant, right? So we will choose. So we will choose, or we'll make sure that the n that we have, we have to make sure that the n that we have is beyond this place. It is sufficiently large. Maybe the n that we have is restricted to this point or something, beyond this big, beyond this rightmost line, because there has to be sufficient gap between Fn and Gn. So we'll choose the n such that it is sufficiently far away to the right, where the asymptotic effect has happened. So these are the three issues, and these are how they are addressed. So now let us see the description of the Turing machine, or more formal description of the Turing machine, right? Of the machine D, whose the language that is in D space Fn is the language recognized by D. D space Fn, but not in D space Gn, right? So what is D? So given an input W, okay, you measure W, measure the length of W. So length of W is, let's say it's n, and compute Fn. Okay, so you compute Fn, and this is why we need Fn to be space constructible, because we want to mark out Fn space. So for that we need to know what is Fn. So for that we need to compute Fn, but then we only have Fn space. That's why we need Fn to be space constructible. So we mark Fn space in the tape, and if the simulation at any point crosses this Fn, so you put a marker or something, if it crosses that marker, you immediately reject. So anything that you compute, this computation will not cross that marker, okay? That is step one. And now you look at the input. So if the input is not of the form, the description of a Turing machine, followed by 1 1 and a string of zeros. So this is 0 star. 0 star means it could be 0 0 0 0 0 0 something. If it is not of the form, this form, a description of a Turing machine, 1 1 and a bunch of zeros, you reject. So it has to be a description of a Turing machine, 1 1 and a bunch of zeros. So the bunch of zeros could be 0 0 or 1 0 or many zeros, more than 1 zeros, right? Now you simulate the machine M. Okay, so there is a description of a Turing machine. M stands for the description of a Turing machine. So the same M, you simulate the machine M on W. So W is M followed, description of M followed by 1 and the many zeros. And see, and while keeping track of how many steps you make. If the number of steps exceeds 2 power Fn, right, we reject. Why do we do that? This is because we want to be more than any GN space bounded machine. So any GN space bounded machine will have 2 power constant GN number of configurations, and therefore that many number of steps. So while 2 power Fn is bigger than Gn, sufficiently bigger than Gn. So 2 power Fn will be sufficiently bigger than 2 power C, constant times Gn. That's why we stop the number of steps at 2 power Fn. Okay, so otherwise how will we know if it continues running, right? So if the count exceeds this, you reject. Now what you do finally is to flip the output. So this is just flipping of the output. If M accepts, then you reject, and if M rejects, then you accept. Okay, so now this may seem a bit cryptic, but all that we are having, so which is slightly different from the time hierarchy theorem proof, is that we have this description of M followed by 1 and a bunch of zeros. So, and then M is simulated. In time hierarchy theorem we simulated M on its own description, but here we are simulating M on the input string, which is the description followed by some bunch of 1 and zeros. So this 1 and zeros, the role it plays is to make the length sufficiently large so that we are in this rightmost region, right? That is the role that it plays, right? And then we flip the output. And step 3 is making sure that it doesn't run too many steps, right? So anything that runs in GN space can be decided in GN space will not take more than 2 power Fn steps. Okay, now what is the language that is in D space Fn but not in D space Gn? It is the language of this machine A. Now clearly what is the space usage of D, right? In order to simulate, so first one point is that M is being simulated by D. So we may require, so the alphabet of M has to be written in terms of the alphabet of D. It may or may not be the same. So that brings in a constant overhead, right? Constant overhead. So C times the space usage of M may happen. So this is, and this is the main overhead. If M uses Gn space, D will use constant times Gn space, where the constant is denoted by a letter C. And in the case of time hierarchy theorem, right, we had a log overhead for the simulation, whereas in the space hierarchy theorem, the overhead is just a constant. And then this is what I said earlier, we want to make sure that we only consider large enough n. So what we do for that, we will choose an n where, so this constant C, right, C times Gn is less than Fn. So we'll choose a constant, or we'll choose n such that C times Gn is less than Fn for all the n above this value. So we will choose all the n to be above n0 where n0 is this cutoff point, where Gn is, or C times Gn is Gn is sufficiently smaller than Fn, or C times Gn is also still less than Fn, and it continues to maintain this continued to maintain beyond that point, and there will be such an Fn because Gn is lid low of Fn. So this is to make sure that the asymptotic effect has kicked in. Okay, so that takes care of the details. And now let us see what happens, the final contradiction, right? So what happens now when the machine D is fed a machine M, the description of a machine M, followed by 0, 1 and 1 repeated n0 times, right? Now in this case what will so now D is not, M is any machine, okay? So M is a description of a machine, so the first step will pass, right? This will pass, and the length is n0 plus 1 plus the description of M, and it will mark sufficient space, right? The space required for this will be Fn, and Fn we know that it is more than n0, right? So n is at least n0, so we have at least n0 once. So f of n will be at least c times g of n. So M has enough space to successfully simulate, D has enough space to successfully simulate M. So D can simulate M and then flip the output, right? So D, when it is fed M, description of M 0, 1 power n0 will be opposite of whatever M does on its own description, or M does on this same input, M description of M followed by 0 followed by 1 power n0. Okay, this is because D has the time and space to successfully simulate M, because the space bound and the time limit is chosen such that the input length is chosen such that the space bound and time limit are respected. Now A cannot be decided in lit law of Fn space, right? This is the contradiction. Why is this? Suppose M is a decider for, suppose of course D takes order Fn space. Now suppose there was another decider M that uses lit law of Fn space. Let's say it uses Gn space. Let's say M is a decider for A that uses Gn space. But we already said that now what happens when D is fed description of M followed by 0 followed by 1 power n0. Description of M followed by 0 followed by 1 power n0 is fed to D. So what we just saw is that D will do whatever, the opposite of whatever M does on this. Okay. So but then now M is supposed to be a decider for the same language as D. But then we just saw that D will do whatever, the opposite of whatever M does. This is a contradiction. So M and D disagree on this input, right? So that is a contradiction. So M cannot be a decider for the same language as D, which means D has to be which means there is the language decided by D, which let's call it A, cannot be decided in lit law of Fn space. So we get the statement of the space hierarchy theorem that D space Gn is strictly contained in D space Fn. Strictly means it is subset but not equal to D space of Fn whenever Gn is a lit law of Fn. Once again, why is it called hierarchy theorem? Because it defines a hierarchy in the space usage. For instance, right? So let's say Fn is Gn is n and Fn is n squared, then we get that D space of n is strictly contained in D space of n squared. And let's say maybe D space of log n, what is this? This is nothing but L, is strictly contained in D space of, I don't know, okay, or maybe why not P space. In fact L is actually contained in, it's even contained in D space of n itself, right? So D space of n is contained in P space. So you could say this as well. So basically there are, for any two functions f and g, if g is asymptotically smaller than f, then there is something that is decided in f space but not in g space. Just a short quick recap of the main idea of the diagonalization. The language that is decided in f space but not decidable in g space is not explicitly defined, but through the construction of a Turing machine, right? So by construction, this Turing machine uses at most fn space, right? So basically it marks off fn space, and then it has a counter that goes up to 2 power fn, but both of them use fn space. And then what it does is, what we make sure is that the input is of sufficiently long length so that the asymptotics have kicked in, so that any input of length gn can be simulated in this space, right? And so we first see that any Turing machine of length that uses gn space, when you feed its own input to this machine, so when you feed the input m1 followed by n0 zeros to d does the opposite of whatever m itself is supposed to do on the same string, right? Suppose this is w, so what d does on w is the opposite of what m does on w, because d is programmed to do that, right? Because d simulates m on this and then does the opposite, right? And right, so now what if m decides the same language as d using lesser space than d? Then by the same argument, d disagrees with m on this input, which means m cannot be deciding the same language as d, and that is a contradiction. So we assume that there is a machine m that decides d using lesser space. That assumption was incorrect, and that summarizes the proof of space hierarchy theorem. So just like we had time hierarchy theorem, we also have space hierarchy theorem, right? So you can do more things